All right, this is Ken Roserer, and my voice is worn out, but you'll forgive me because hopefully this video will help you. This is how to use the rational zeros theorem to find zeros of a polynomial. So first thing we got to do with this, after reading the question, we see that there is at least one rational zero. And based on that, we should be able to reduce this polynomial by 1 degree if we find it. So how do we find it? Well, first we list all the possibilities. So the possibilities are going to be factors of the lead coefficient um, divided into factors of the final constant. So better way to say that, factors of the constant divided by factors of the lead coefficient. The constant only has 3 factors. The lead coefficient has 3 factors as well. Actually, it has 6 here because all these are plus or minus. What I have invented just a couple minutes ago is this method for doing this. Um, it's not really my invention, it's just a way I thought of. Okay, here we go. I'm going to write factors of the last guy, the constant at the end. I'm going to write factors of the lead coefficient on the side, and I'm going to put little division signs in here. On the top of the division signs, I'm just going to write 1, 2, 4, 1, 2, 4, 1, 2, 4. Basically these results just going down. Underneath, I'm going to write whatever factor I have over here. So 1 over 1, 2 over 1, 4 over 1, 1 over 3, 2 over 3, 4 over 3, 1 over 9, 2 over 9, and 4 over 9. Those are all my possible factors. Some of them are repeated though, maybe. Let's look. That's a 1, that's a 2, that's a 4. 1/3, 2/3, 4/3. 1, 9, 2, 9. No, none are repeated. So we have 9 times 2, 18 possible zeros. Are we going to check them all? No way. We're going to work our way through these easy ones first, the 1, the 2, and the 4, plus or minus, and see if they work. So if we want to do h at 1, we plug in a 1 everywhere. And we check if it works. Because we're plugging in a 1 everywhere, we just end up adding the coefficients. And we see, nope, that's positive, right? So 1 is not a 0, which means x minus 1 is not a factor. Okay, so that's not going to work. If I do negative 1, I can plug in a negative 1 everywhere, but the only thing plugging in a negative 1 will do is change this to a negative. That'll still be positive, and that'll be, it was negative, it'll become positive, right? Because when I go 9 times negative 1 cubed, don't I get negative 9? And when I do 9 times negative 1 squared, that becomes a positive, so that 9 doesn't change. Negative 16 times negative 1, positive 16, and plus 4, plus 4. So you can see a negative 1 will change the coefficients of terms that have a odd degree to the opposite sign. And well, let's just add these up real quick and check if it comes out to a 0. No, it doesn't. It's also positive, right? So no 0 there, no 0 there. What's the next number we're going to try out? 2. So we'll try out positive 2, and hopefully it'll work. If it doesn't, then we'll try out negative 2. So once again, I can write out the function and I can go h of 2 equals, blah, 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 9 times 2 squared plus 2 cubed plus 9 times 2 squared minus 16 times 2 plus 4. I can do it that way, or I can use synthetic division, which is put a 2 up here, write down the coefficients, and if you get a remainder of 0 in the box on the bottom, then you know that 2 is a root and x minus 2 is a factor. I like doing it this way better, because if you do it correctly and this comes out to 0 down here, then what's over here will be your quadratic reduction of this cubic. And we'll talk about that if that happens. So I bring down the 9. 9 times 2 is 18, so I write it 18. 9 plus 18 is 27. 27 times 2 is 54. 54 and negative 16 is positive 38. And then 38 times 2 is 76. And when I add that, that's 80. Does it work? No, and it's positive. So that doesn't work either. Let's try negative 2. Same process. 9, 9, negative 16, and 4. Just before I go on, let me double check that I wrote down the equation right. 9, 9, negative 16, and 4. Okay. So first step to synthetic division is to bring down the lead coefficient. 9. 9 times negative 2 is negative 18. 9 minus 18 is negative 9. Negative 9 times negative 2, positive 18. 18 minus 16 is positive 2. 2 times negative 2 gives you a negative 4. And when you add those, you got a 0, which means what? Negative 2 is a 0, which means x minus 2, or x plus 2 rather, is a factor, and the other factor is 9x squared minus 9x plus 2. That's our other factor. And once we have one of the factors giving us one of the zeros, to find the other two, isn't that a quadratic? 9x squared minus 9x plus 2. So can't we find the last two either by factoring that or using quadratic formula? So I'll do it by factoring, but if you don't know how to factor, you can use quadratic formula. I'm going to look for 2 factors of 9 times 2, 18. That add up to negative 9. So they have to multiply to give it 18. They have to add to give a negative 9. And the two numbers that do that are negative 3 and negative 6. Negative 3 times negative 6 is 18. Negative 3 plus negative 6 is negative 9. And so my result is 9x squared minus 3x minus 6x plus 2. Basically what I did there is and you should hopefully know how to do this if you know how to factor, is I rewrote the negative 9 as negative 3 plus negative 6. All right, and having done that, I'm going to factor by grouping. I can pull out a 3x here. Leaves me with a x, minus 1. Let me fix that. Pull out a 3x, leaves me with a 3x minus 1. I can pull out a negative 2. Also leaves me with a 3x minus 1. And I'm happy because these guys match, which means my factorization is 3x minus 2 times 3x minus 1, which means my last two roots are found by setting those factors equal to 0. So x equals 2/3 or x equals 1/3. And you could get the same results using quadratic formula. It'll take you right to those two answers. So my final answer then is, let's see, I had 3 roots. One was 2/3, one was 1/3, one was negative 2. So my answers are negative 2, 1/3, and 2/3. Those are the zeros of this polynomial. And that's it. That's how it's done.